Okay, we are back with a new background, and I'm excited about that background. As I told the audience, the students here, that if you want to find out what this background is and how we generate this fascinating set of hexagonally placed doilies, then you need to take my course on multidimensional signal processing, which, by the way, is already online if you're if you're so inclined. Okay, let's go ahead and start. I suppose that we can start with the homework, and I wondered how you were doing on the homework. I think that today's lecture is going to make it easier for you to do the first part of the homework. I'll talk about that just in a second. Okay. Well, guess what? I shared the wrong thing. I was multitasking and I clicked the wrong clicker. Okay, this time I clicked the right clicker. Let's see. We have the homework about calculating the mean autocorrelation and autocovariance of X. Has anybody done that successfully or unsuccessfully? Okay. Hopefully by the end of today, we will come up with some results and you will see that it's relatively easier to do than you might imagine. So let me unshare. Okay. And anybody do from the ensemble? You guys are near the end of finals. Okay. I can see what I need to give for a final examination question here. Okie doke. Well, that's fair. So we really have nothing to talk about here as of today. So
I have a question regarding number two. So I was looking for inspiration, and so I went to Wikipedia, and they talked about for a discrete signal, which is what we'll presumably be working with when we do the computer work section of this. They talked about using a Fourier transform, and you Fourier transform the signals into Fourier space, and then there's another way to obtain the autocorrelation. Is that the method of estimating the autocorrelation function that you're looking for?
We will find out that indeed we can use Fourier transforms to compute the autocorrelation. But see, there's the assumption here, and we haven't gotten into this, that the underlying process must be correlation ergodic. In other words, there's two different ways that we generate these means. One is through an ensemble. Another one is through a single observation. And remember, through a single observation, we have to have this property of ergodicity. And it does turn out that the process that we're looking at is ergodic, correlation ergodic. But I'm asking you to compute it using the ensemble, because I want that understood. And if you do look back in the lectures, you will find out that we've already done this. To kind of refresh you, what we did is we assumed a white uncorrelated stochastic process, and we showed that the correlation should be in a matrix, just a constant on the diagonal and zeros off. Do you remember that a little bit? And then we showed a graphic where that was experimentally determined, and indeed that was the case. So, okay, hopefully after this lecture, we should be able to see the results a little bit better. So let me go ahead and get into the lectures here. And Theo, to answer your question, I'm not familiar with what the Wikipedia article you're talking about, but yes, there are a number of ways to compute the autocorrelation under the assumption that it's correlation ergodic. Today, I wanted to talk about analytic and processing of random signals and filtering. We are all familiar with bandpass signals and bandstop signals and all other sorts of signals. And we would like to know what happens when we filter these processes. The first thing we'll do is we will talk about putting a non-stationary process, x of t, through a linear system. First of all, let's recall what we did for a one-dimensional deterministic signal. We put x of t into a linear system. Now, this is not time invariant. It's a linear system. and the output is y of t. Now, linear, if you remember, assumes additivity, that the sum of the responses is the response of the sum. The sum of the responses is the response of the sum. And then homogeneity, which assumes that if you amplify the input, you will amplify the output. If indeed your system operates on both of these, or satisfies both of these criteria, your system is linear, additivity and homogeneity. You should remember this from undergraduate systems theory. So let's now assume that their signals are not deterministic, but they are stochastic. So we put in a stochastic process into a linear system and we get out a y of t. It does turn out, as you might expect, that the expectation and linear operators commute. So we have no problem of interchanging the operations of a linear operation and an expectation. So here on the bottom is the mathematics of what I just said, that the expected value of a linear operator is equal to the linear operator on the expected value. This gives us a lot of mileage in messing around with things. So let's recall what happens if we have an LTI system. Besides being linear, it is also time invariant. In that case, the output is equal to the input convolved with the impulse response of the system, which is an h of t. On the bottom here, you can see written what? Where's my thing? Yeah, on the bottom, you can see written the so-called convolution integral. So if you have h of t, you can take your impulse response, stick it in your pocket, go home, and you have the output designed for every possible input, which is kind of cool. The other cool thing about this is that when you're taught about convolution, you go through all of these convolutional results, and then you find out, lo and behold, that you don't have to do the convolution. The convolution in the frequency domain is multiplication. And so we can convolve in one domain by multiplying in the other domain. Now, this is for a deterministic signal, and we have to be careful here because I'm using y, capital Y, in two different cases. Here I'm using y as the Fourier transform of little y, and I'm using big X as the Fourier transform of little x. And this also is denoted by, or the capital Y also corresponds to a stochastic process. So we're having a little bit of ambiguity in our notation here. Here it means Fourier transform. And I think in the context of our presentation, we'll see that if it relates to, excuse me, if it relates to a Fourier transform or possibly a stochastic process, we're using the same notation for both. So here we have a stochastic input into a deterministic LTI system, linear time invariant system. So with the input and output, we have this result. We have that y of t is equal to x of t convolved with h of t. We're assuming that the system is deterministic, so h of t is a deterministic function. And here the capital Y's and x's still refer to the stochastic processes. So we get this convolution, and this convolution is going to give us a stochastic process. It's the stochastic process x convolved with the impulse response h. So before we consider the linear time invariant case, let's consider just the, you know what, that shouldn't be there. I don't know why this is in the slides. I think I meant that to be a linear time invariant system, but that's not what we have here. So now we're going to take a stochastic process, x of t, And we're going to place it into a linear system. Not time invariant, but linear. And we get a corresponding output y of t. So for this general case, we're not assuming that x is stationary. And we're not assuming that the linear system is time invariant. This is a time varying system. So we got a lot of variations going on here. Your stochastic process can vary and your system can vary. So let us start with the cross correlation. We're going to do the cross correlation between x and y. I'm sorry, that should have been there. I apologize. No, this is an LTI system. So forget what I said about linear. It's also, well, it is linear, but it's time invariant. So what happens here is that if the system is linear and time invariant, if the system is linear and time invariant, and again, I apologize for introducing it incorrectly. Apparently, I didn't review the slides closely enough before the class. But if it is a linear time invariant system, then the cross correlation between the input and the output is equal to the expected value of x of t, excuse me, times y of tau. So therefore, if x of t is like this, and you look at a value here, this is going to be a random variable. And if we look over here at y, and y is some sort of output, you're going to have a statistic here which corresponds to the output of y at tau. So what is the expected value of this number times this number? Or I should say the expected value of this random variable and the expected value of this random variable. So this is going to be y of tau, and this is going to be x of t. So it's the expected value of x of t times y of tau. Again, if we were to use complex system, this would be conjugated, but we're just considering real systems here. Well, we know that y of t here is equal to the input convolved with h of tau, correct? So this is really nice because what we can do is write out the integral for the convolution integral and then recognize this is equal to the expected value of x of t times x of alpha. And this is going to be integrated from minus infinity to infinity. Of h of t minus alpha. Now, the thing in the brackets is recognized as r sub x of t alpha times h of t minus alpha. So the thing in brackets is recognized as the autocorrelation of the input. Now, this is a little bit of a tricky integration, but it's not that bad actually, because let's just assume here that t is a constant. The t is a constant here, and t is some sort of fixed number. If we assume that t is some sort of fixed number, we recognize that we have a convolution here with respect to the variable alpha, or the variable t, either one. This should be a tau, by the way. Sorry about that. Tau. So it's a convolution of this, of h of tau with r sub x of t tau, where we assume that the first variable t is a constant. And so you can think of it as this way, as shown in the bottom. It's the autocorrelation of the input convolved with respect to tau, because we have to specify whether it's a convolution with respect of t and tau. We're just going to keep tau exactly the same, and we're going to perform the convolution with tau. You can think of this in the following way. Think of this as r sub x of t and tau. Now, this is a two-dimensional function, right? And let's assume that tau goes this way and t goes this way. So we have a two-dimensional function. In discrete time, we would assume this is just a big matrix, if you will. What we're saying is we take this rho, which is a function of tau, and we convolve this with h of tau. And then when we convolve it with h of tau, what are we going to get? We're going to get a new line here, won't we? It's going to be t in this direction, and it's still going to be tau in this direction, but the signal across this one line, this one slice, if you will, has been convolved with h of tau to give us this slice over here. And we do that for every horizontal slice, every horizontal row. So we would take this result, would convolve it with h of tau. Notice that this dashed line is a function of tau. So we take this one line, whatever this function is, convolve it with tau. So you can think of this as being a big matrix and then taking all of the rows and each row convolving it with h of tau. Is that okay? And then what we get over here, according to this relationship, is the r sub xy of t tau. R sub xy of t tau. So again, you take r sub x, you convolve it in one dimension with respect to tau for every single row, and you get out the cross correlation. You get out the cross correlation between the input and the output. So that's interesting. So we have the again, the big takeaway here is that r sub y of t and tau. I'm sorry, r sub xy. The cross correlation is equal to the input correlation convolved with respect to tau of h of tau. In other words, we convolve with every row, the same value. So we okay here? So this is the takeaway from this slide. But really what we're interested in is not the cross correlation. It's interesting, but we would like the autocorrelation of the output here, y of t. We would like the autocorrelation of the output y of t. So let's figure it out. So here's our problem again, x of t going into an LTI system and getting an output of y of t. X of t is not necessarily stationary. Now, what we're looking for is the autocorrelation of the output here. This is the autocorrelation of the output. Now, we have determined that we can write y of t as the convolution of x of t with the impulse response, right? And we're going to leave y of tau the same. And we're going to do this for a reason. The reason we're going to do this is because now we have the expectation of this integral. If we take this convolution and we write out the convolution integral, we get this expression which is shown here, x of t convolved with h of t. Now you can see what happens as we take the expectation on the inside. What do we get? We get the expected value of x of alpha times y of tau, right? So we can write this then as the integral of what? R sub xy of t and tau times h of t minus alpha. H of, is that right? T tau, yes, H of t minus alpha, yes, d alpha. So this is all well and good. And the interesting part here is, of course, that this is recognized as a convolution. Now, before we kept tau constant, we're going to keep tau constant right now and just look at t. So tau is a constant and t is a variable, and we're convolving this thing with respect to t in the t direction. So this is h of t, so we can express this integral as h of t convolved in t, in other words, convolved with respect to the first variable, assuming the second variable is a constant, and that then gives us the autocorrelation of the output. So through a two-step process, we've done something interesting here. We have computed the autocorrelation of the output as a function of the cross correlation of the input and output. Right? That the autocorrelation of the output is related to this cross correlation between the input and output. Now, the reason this is cool is that we have already computed what r sub xy is in the previous example, and so we simply need to plug that in here to get an interesting example. So this is just like before. We have a two-dimensional variable r sub xy. And let's see, if we let t go in this direction now, and tau go in this direction, every row here, if we take every row and we convolve it with h of t, we are going to get a row of r sub y. So we take this row, convolve it with h, we get a row of r sub y. We take this row, we convolve it with h of t, we get the row of the autocorrelation on the output. So it's very similar. So again, the idea is to take our previous result for r sub x of y and substitute it in there for from the cross correlation, and let's see what we get. We just derived this expression. This is the expression we derived. The autocorrelation of the output is equal to the cross correlation convolved in the t dimension. But then we showed that the cross correlation is equal to the input convolved in the tau dimension. So the final result is that, let's see, r sub x, y, t tau. That looks to be the same as the top expression. I don't know why I repeated it. So this is the result. The autocorrelation of the output is equal to the autocorrelation of the input convolved with the impulse response with respect to t, and then with respect to tau. So what we do is we take the r sub x, and then we convolve it each row, and then we get the r sub xy, and then we convolve each column. Sorry, I'm going to be overwriting here. We convolve with each column, and we get the corresponding autocorrelation of the output, r sub y. So does that make sense? We take each value of the row and each value of the column for r sub x, and we convolve each row with r sub x. Then once we get done, we convolve each column with respect to r sub x, and that gives us the autocorrelation of the output, the two-dimensional autocorrelation. So that's kind of cool. Here's the important point, though, that we can take a non-stationary stochastic process, and that's what x of t is, right? It has an autocorrelation, which is a function of both t and tau. So we can take a simple non-stationary stochastic process, and if we know the autocorrelation of the input and we know the impulse response, we can figure out the autocorrelation of the output. The bottom line, and we'll see this as a recurrent theme, is that the second order statistics are preserved as we go through a linear time invariant system. So we can take a stochastic input. If we know the correlation, we can compute the autocorrelation of the output. And then if that's fit into another linear system, we can compute the autocorrelation of that output. So second order statistics are able to be transferred through linear time invariant systems without much of a problem. There's just a little bit of mathematics to do as we perform convolutions with respect to tau and t, the two variables of the autocorrelation. So this is all well and good and kind of interesting. We're more interested, more interested, but we're going to get more power if we have a linear time invariant system. For example, if you recall, power spectral densities are Fourier transforms of autocorrelations. We're assuming a one-dimensional autocorrelation, and the one-dimensional autocorrelation only occurs when we have a wide-sense stationary stochastic process, right? So we can't talk about power spectral densities here because the process is not stationary. The idea of a power spectral density for the case we've analyzed, this general case, is not applicable. It's not applicable. Let's look at an example before we get into stationary processes of differentiation of random processes. Now, the mathematicians will get a little bit picky here because they say that not all random processes are differentiable, but let's just assume they are. If they are indeed, if we convolve, if we differentiate, first of all, with respect to the tau variable, and then we differentiate with respect to the t variable, this is the result that we get out, right? Differentiation, by the way, is a linear time invariant process. Differentiation is a linear time invariant process. But the process here, the autocorrelation itself, need not be stationary. It need not be stationary. So if we have a stochastic process, we want to compute the autocorrelation of the output after differentiation. We first of all differentiate all of the rows of the autocorrelation, then we differentiate all of the columns of that result, and that will give us the autocorrelation of the output. So this then brings us to the area of stochastic differential equations. Doesn't that sound like fun? Indeed, I showed you the equation for Brownian motion, which is a stochastic differential equation that's used a lot in finance. And stochastic differential equations occur when you have a forcing function in your differential equation that is a stochastic process. What are you going to do with it? Well, one of the things we'll find out is that we can trace through the autocorrelation with a stochastic differential equation. Here is a stochastic differential equation. On the right are derivatives of the input, and they're related to derivatives of the output on the left. And you have seen these sort of things in, for example, control systems where they place these relationships in a matrix form. AX plus BU is equal to C or something like that. I forget what it is, but you can always place these into state equation form. You familiar with what I'm talking about here? Okay. So the question is, what if you have what happens if your control system is being subjected to a stochastic input? What does it do? How do you trace it through? We're going to trace through the autocorrelation. There's other things you can trace through, but we're going to do this. We're also going to assume no particular solution. Do you remember differential equations have a natural response in accordance to initial conditions? We will assume that all of the initial conditions are zero so that we don't have to look at natural responses. For example, if you have a circuit and you have a capacitor that's initially charged up, you have to take into account the voltage across that capacitor in solving the differential equation. You have a separate solution, which is called the particular solution to the differential equation. We're not going to be considering the particular solution. So given a non-stationary correlation of X, find the particular forced solution for Y of t. I think I goof this up. Let's see, we want a forced solution, not the, okay, so I guess I got my terminology messed up here. The particular solution is the forced solution. We're going to have no responses due to initial conditions. So let's look at R sub y of t. That's what we want to find. We want to find the autocorrelation of the output y given the autocorrelation of x. It's actually relatively simple. And just like before, we'll find a little stepping stone where we find the cross correlation between the input and the output of the stochastic differential equation. Yeah, if you go back to circuits and you apply Kirchhoff's laws, remember Kirchhoff's laws? You get equations like this that satisfy the differential equation or satisfy the circuit, and you have to solve those. So here is the original result. Here's what we're going to do. We're first of all going to figure out the cross correlation. And we're going to do that by multiplying both sides of the equation by x of tau. You notice that on the top equation, there's no taus there. There's no taus on the top of the equation. But we can multiply both sides by x of tau, which we have done here. And then can you guess what we're going to do next? We're going to expectate. I don't know if that's a word, but if it isn't, it should be. We're going to take the expectation, or we're going to expectate both sides. And if we expectate both sides, we get on the left, we get the autocorrelation, because what's the expected value of this? It's equal to the expected value of x times y. That's the cross correlation between x and y, right? And if you do it on the left here, you get the expected value of this, which is equal to the autocorrelation of the input. So as before, we have the cross correlation here as a function of the input. Now, at this point, notice there's nothing stochastic, is there? Everything is deterministic. The correlations are totally deterministic. So you can solve this equation the way that you would solve any other equation. You would first of all assume that tau is equal to a constant, because you notice all the differentiation is with respect to t. So kind of keep tau as a tag-along constant. And then you have a simple differential equation, which you can solve by Laplace transforms or some other technique in order to compute the cross correlation. Again, tau just goes along for the journey. There's nothing that operates on tau, so it's just a constant that's carried on. So we're going to assume that you can solve this differential equation and you can get r sub xy tau, or r sub xy, the cross correlation. Now here's our original differential equation, and this is the differential equation that we solve for the cross correlation. And we will assume in the solution of this differential equation that all of the initial conditions are zero. And this is equivalent to, by the way, the bottom equation. Because if we assume that all of the derivatives are equal to zero, this means no charges on any of the capacitors or anything like that. Since this is equal to zero because of the initial conditions, because of the stochastic process, all of these values are equal to zero. And if we perform an expectation on the left side, we get the right side, and that means that in the solution of the differential equations, we also assume these boundary conditions, which are shown here. So all of the boundary conditions are zero, which is a good way to solve a differential equation. This gets rid of all of the natural solutions. That was the term I was looking for, natural solutions, which is just due to the initial conditions. Now we'd like to find the autocorrelation of y. We start with the original differential equation before we multiplied both sides by x of tau. Now we're going to multiply both sides by y of tau. Again, notice that there is absolutely nothing here which is going on that is a function of tau. So tau just carries along as just a constant. Then we perform an expectation of both sides. Expectation is a linear process. And so on the right side, we get the expression, the result, expected value of y of t, y of tau. What is that? That is the autocorrelation. On the right side, we get y of t, the expectation of here. What's that? That's the cross correlation. You'll notice here that I have something deleted. I have the B sub n's. So these should be carried forward in some way. They were omitted in the slides, okay? So we have another differential equation. Again, notice that the differential equation is with respect to t. Tau is just carrying along as a constant. So we don't have to worry about tau in solving these differential equations. Tau is simply a constant. So again, we can solve this differential equation and by Laplace transforms or whatever technique that you would like. And here is the cool part. What is this? This is the cross correlation, which we computed in the first step. And so we know that. We've already solved that first differential equation to get the cross correlation. So now we have this function as a forcing function, which allows us to solve for the entire autocorrelation of the output. I'm sorry for the scribbles. I can't see where my cursor is at, so I got to scribble sometimes to see where it's at. So that's it. That's kind of cool. So the point is that for a stochastic differential equation, if you're given the autocorrelation of the output or the input, you can generate the autocorrelation of the output by solving differential equations. It's a little bit more complicated, but you can solve differential equations. Again, I would point out that this differential equation is totally deterministic. There is nothing stochastic in there. The autocorrelation is a deterministic function which describes the autocorrelation or cross correlation. So this is all well and good. And so here we go again. This is a summary. We find the particular solution, and we are assuming this, and then the differential equation as before has all zero initial conditions if there were no initial conditions associated with the circuitry or whatever system you were trying to solve. So we have this, we solve two differential equations with the assumption that all of the initial conditions are zero. And the two solutions are, first of all, finding R sub x here, finding R sub x, finding the cross correlation given this. So in this case, this is given. And we need to find the cross correlation here, again, by using conventional techniques for solving these Laplace transforms or whatever. And then we have a second equation where now we have a forcing function R sub xy, the cross correlation, but this cross correlation has been computed in the first step. The cross correlation has been computed in this first step. And so now we have the second differential equation, and we need to figure out what the autocorrelation of the output is given the cross correlation. And we can do this again using things like Laplace transforms and things of that sort. In both cases, tau just goes along for the ride. In both cases, tau just goes along for the ride. So that's kind of interesting. And here's the initial conditions for the correlation. I'm sorry, the autocorrelation of the input. Okay, so what we've just explained is solution of a stochastic differential equation under the assumption that we feed the stochastic process through a linear time invariant system. And the result that we get is very nice. the result that we get is that we can trace through the second order statistics, specifically the autocorrelation, by solving differential equations motivated by the differential equation of the original circuit. So again, we see that as we've seen in the cases before, the linear time invariant systems are very nice in the sense of tracing through the second order statistics. And we can generate second order statistics, autocorrelation with these differential equations. So this is very nice, especially for engineers, because we see that these second order statistics in the case of stationarity begin to relate to something like power and such. So with that, let's go on to the case of filtering wide sense stationary random processes. Before, we did not assume stationarity. Now we're assuming stationarity, at least in the wide sense. Mathematically, this corresponds to the autocorrelation just being a function of one variable, being a function of tau. Let's first of all figure out what the mean is. Here is the expected value of the output. So here's the expected value of the output. Well, it's equal to the expected value of the convolution, right? Because the output is equal to the input convolved with the impulse response. The only thing that's stochastic here is the input, and we do the expected value of x of t, and the expected value of x of t is what we will call the mean of the stochastic process. So the output has a mean, and that mean is convolved with h of t. Well, lo and behold, the mean is a constant if we're a wide sense stationary stochastic process. Remember, the mean is a constant, and the autocorrelation is just a function of the difference of two variables. It's a one-dimensional function. So therefore, we can take this expectation outside, which we see here, and we get this integral h of tau d tau. If you remember the frequency response of a linear system, and now we're using Fourier transforms in this course in three ways. We're using them, number one, for the characteristic function. We're using them, number two, for the power spectral density. And now, number three, we're using it to Fourier transform the impulse response to get the frequency response. So these are three independent uses of the Fourier transform, and sometimes it's difficult to differentiate between them, no pun intended. So h of f is equal to the inverse the transform, and not the inverse, but the regular transform of e to the minus j 2 pi f t dt. That's the Fourier transform. So if you look at h of 0, f is equal to 0, you get that for f is equal to 0, this whole term disappears, right? It goes to 1. For f is 0, the second term totally goes to 1, and we are left with the area under the impulse response. And this area under the impulse response is exactly the function that we have here. So maybe in terms of the frequency response, it's just easier to talk about the frequency response evaluated at the origin. But here's the cool part. If the input has a constant expected value, the output will have a constant expected value. And that constant expected value is equal to, say, m sub y. So that's kind of cool. One of the aspects of wide sense stationarity is that the mean is always a constant. So we've met one of the criteria for a wide sense stationary stochastic output. And what we'll find out is if you have an LTI system and you input a stationary stochastic process, you will get out a stationary stochastic process. Plus, we can map through the system those first and second order statistics, if you will. Okay, if the input is wide sense stationary, so is the output. We've already established that if the input is a constant, then the output is going to be a constant in terms of the expected value. So here we go. what is the autocorrelation of the output? You notice here that I'm making an assumption already. I'm assuming that the output is already stationary. So I'm assuming that that's the case here. What I'm going to do is go ahead and crank through this and show that this is indeed justified. So let's go ahead and crank it through. So again, this is an assumption on my part. To take the expected value, we need to do the following. We need to do the convolution here in order to get this value of y of t. And then we need to do the convolution here in order to get this y of t. Then we shuffle things together. The only thing stochastic in here is this x and this x. Everything else is deterministic. So we only have to take the expected value of what is stochastic. And here, if the input is wide sense stationary, then the autocorrelation is independent of t. It's only interested in how far you are separated from each other. So because it's not a function of t, this output, because the input is wide sense stationarity, the input is wide sense stationarity, so we can write it this way. It's not a function of t. Now, we have a little bit more of analysis to do, but right here, we can see wonderfully that the autocorrelation of the output is not a function of t. The t has totally disappeared in the equation. The t has totally disappeared in the equation. So therefore, the output is indeed wide sense stationary. So again, as you can see on the top, if the input is wide sense stationary, so is the output. And in fact, we can go through and we can trace the wide sense stationary second order statistics through the linear time invariant system in order to get the second order statistic output. Now this, though, on the bottom is a little bit complicated. The cool part is if you turn the crank on this final equation, you'll find out something really cool. And that's in terms of the power spectral density. The power spectral density of the output on the bottom equation you can see here, the power spectral density of the output is equal to the power spectral density of the input times the magnitude squared of the impulse response. I'm sorry, of the frequency response. I said impulse response, I meant frequency response. So this is the cleanest way, I think, of figuring out how the second order statistics go through the linear time invariant system. This is how they go through the linear time invariant system. So there's two equations now. The first one is the expected value of the output is equal to the expected value of the input times the frequency response of the origin. That's what we're doing here. So if the input expected value is a constant, so is the output. And down here, we're tracing through the power spectral density, which is equivalent to the autocorrelation. Why is that? Because we can inverse both sides here. And if you remember, R sub x of tau, which is the autocorrelation, is such that the Fourier transform of R sub x of tau is equal to S sub x of f. The Fourier transform of the autocorrelation is equal to the power spectral density. But just like in convolution, you can get the output by taking the input and convolving it. That's fine. Or you can Fourier transform the input, multiply it by the frequency response, and get the Fourier transform of the output, right? And this is kind of the equivalent way of doing it. It's easier to think about how the second order statistics are transformed through the system in order to, it's easier to think about this in the frequency domain as opposed to the time domain. Now, something happens similarly for a discrete time system. It turns out that the same thing happens, except that the Fourier transforms are discrete time Fourier transforms. So you have discrete time Fourier transforms, and the expected value of the output is equal to the expected value of the input. And the power spectral density is related in the bottom equation here, which you see is the same form as it was for the continuous case. So in both cases, we're not surprised that these first and second order statistics map through, and they map through very nicely. So let's take a look at some examples here. Let me check my time. Okay, I got a little bit of time. Let's assume that we have zero mean white noise. Notice not white Gaussian noise, but white noise. What is white noise? It has an autocorrelation of a Dirac delta, and it has a power spectral density of a constant. So if we put white noise, x of t is white noise, into an LTI system, the output is going to be sculpted, and the expected value of the output is always going to be zero. Why is that? Because the output is equal to h of 0 times the mean of the input, the expected value of the input, but the input has zero mean. So this is going to be 0. So the output of the stochastic process is going to have an expected value of 0. And I think you can see here that if the input, that if the power spectral density of the input, S sub x, is equal to a constant, usually they talk about this constant as n naught over 2. So if the input is a constant, then by the expression that the power spectral density of the input is equal to the power spectral density of, the power spectral density of the output is equal to the power spectral density of the input times the magnitude squared of the frequency response, then you can see if we multiply these two together, we get the expression which is shown here. So this is an example of when the input is white noise. This traces through the first and second order statistics very nicely. We can talk about low pass, high pass, and band pass filters. That's what we do in signals and systems, especially with applications. And in all cases, the correlation of if the power spectral density of the output is equal to the power spectral density of the input times the times h of f. The question is, where did the h squared go? Well, it turns out if you're talking about a low pass filter, we're going to assume a ideal low pass filter, which in terms of frequency is something that looks like this. But the important thing is that this low pass filter has an amplitude of 1, right? So if this is my h is the same thing as the magnitude of h squared, right? Under the assumption that the magnitude of the low pass filter is equal to 1. Because 0 squared is 0 and 1 squared is 1. In a similar fashion, if we have a high pass filter, say a filter that goes like this, we're also assuming that the value at the origin is equal to 1. So assuming these filter parameters, h squared is going to be the same thing as h. Same thing for a band pass filter or a band notch filter, whatever. If I assume the amplitude is equal to 1, then this holds out, but only under the assumption that the magnitude is equal to 1. One of the things which we haven't proved is that the power spectral density is always non-negative. And we can do that now. if we have an output, let's say that we have this input here. This is an input, and this is a bandpass filter. And this bandpass filter is over an incremental bandwidth from f sub naught to f sub naught plus a little bit of slop, okay? So that's the bandpass filter. It's a very narrow bandpass filter. So what is the output then? The output will be, as we saw before, since this does have an amplitude of 1 here, this does have an amplitude of 1. It's equal to S sub x times h of f, right? And if we apply this, the expected value of the output of the stochastic process is equal to r sub x of 0. This is the power associated. Remember that if we integrate over the power spectral density, we get the average power, right? So if we look at the expected value of y of t squared, which is exactly the same as r sub y of 0, we're going to get s sub x of f df. In other words, it's just going to be, we're multiplying this by x sub x. So the power spectral density of the output is going to be over this little band here. The output spectral density is going to be over that little band there. And if the df is small enough, this value, which is s sub x of f naught, assuming that this d sub f is small enough, we can approximate the area of this by the height, which is s sub x of f naught, times the width, which is df. And this always has to be greater than 0. So the average power delivered by the output in this one little increment, in fact, in any little increment of the power spectral density, must be non-negative. So that must be true for this little interval, this little interval, this little interval, all the little intervals. It must be equal to something which is non-negative. I think I said positive. I really rigorously meant to say non-negative because it can go to 0. So this is the proof that the power spectral density is always greater than or equal to 0, because the power of a stochastic process is always greater than or equal to 0. Let's look at filtering wide sense stationary random processes using derivatives. We're going to assume that the stochastic process that's wide sense stationary is differentiable. And let's just do the derivative. Now, if you recall from Fourier transforms, if you perform a derivative in the time domain, in the frequency domain, that's equivalent by multiplying by J2 by F. Do you recall that? Okay. So again, differentiating in the time domain means correspondingly to multiplying in the frequency domain by J2 pi F. Or if you're an omega man, it was J omega. You multiply by J omega. So the expected value of x of t, well, let's see, that's equal to the mean of the input times h of 0. Well, what's h of 0? 0, correct? And that makes sense, because if you have a stochastic process that kind of meanders along over a constant, you're kind of getting rid of that constant. It's like differentiating a constant. At least that's the flavor of what's going on. And the power spectral density is 2 pi f squared times s sub x. So this is equal to what? That's equal to h squared. Notice the j goes away since we're taking the magnitude of h as opposed to h squared. We're taking the magnitude of h squared. And if we Fourier transform and inverse Fourier transform, we find out that the autocorrelation is given by the expression here. This is very interesting. The output autocorrelation is equal to minus the second derivative of the input. Now, why is this interesting? I'm glad you asked. This is interesting because you remember the autocorrelation must be very special. It must be maximum at the origin. It must be for real signals even. Now, what happens if we differentiate this once? If we differentiate this once, this is going to look like the following. It's going to look like the following. If we differentiate it twice, what's it going to be equal to? It's going to be equal to something. Well, let's see, if we differentiate it twice, I'm trying to do this in my brain. This is a negative slope, right? And this is a negative slope. So it's going to be something like this. So I'm going to call this R sub x double prime. Notice, by the way, if you differentiate an even function, you get an odd function. If you differentiate an odd function, you get an even function back, right? So this is R sub x double prime. Well, this is all well and good, except it's flipped upside down. But lo and behold, we have this nice minus sign here. And this minus sign flips us back up. And so we're into a very nice R sub y, which again satisfies all of the properties of autocorrelation. So I think that that's kind of slick. It's kind of a little sanity check here on what happens with the derivative if we differentiate a stochastic process. Okay, the last is ARMA. I'm not going to go into ARMA because it's not as interesting. So the final result summary, if we have something going into an LTI system and it's a wide sense stationary system, then the output, the expected value of the output is the expected value of the input times the frequency response at HO. That's this equation. And then lastly, we have the power spectral density relationship, which is shown here. And so that's the big takeaway from all of the math that we've done so far. Okay, with that, are there any questions at all?
No, but I think it's interesting that we've kind of proven what I think is somewhat intuitive with regards to filters and their effect on power spectral density.
Yes. Yes, but it isn't times the frequency response, it's times the magnitude squared. And you notice the power spectral density has to be non-negative, right? So if you start out with something non-negative, you have to multiply it by some non-negative to make sure that the end result is non-negative, right? And that thing we multiply it before, which is the magnitude squared of the frequency response, is non-negative. So we're good. So we're conserving the properties of the power spectral density there.
That made sense because I had forgotten that you could potentially have a negative frequency response, I think.
Well, yeah, the idea of negative frequency has always baffled me. And I've written entire textbooks on Fourier transforms, and it's just an anomaly of the Fourier transform. The negative frequencies don't exist. The closest I can get is whistling. A positive frequency is when you whistle, and a negative frequency is when you inhale. It's as close as I can get. But I think that probably has nothing to do with positive and negative frequencies, but that was kind of, that amused me with that interpretation. But it does turn out anytime you deal with real signals, and the world is a real signal, that you always have this Hermitian symmetry. That you always have a Hermitian symmetry, Hermitian or conjugate symmetry, which means if you take one side of the Fourier transform, you flip it around and you conjugate, you get the other side. So only one side of the frequency is really responsible for the whole spectrum. For a real signal, if you only know one side of the spectrum, you know the whole spectrum. You don't have to worry about the negative frequencies because they're a given. Now, where you get asymmetry and where it no longer applies is in the case of complex signals. With complex signals, you no longer have to have a Fourier transform that is nice and symmetric or conjugately symmetric. Rather, that Fourier transform can, be really weird on one side and really weird on the other side. But for real signals, and we usually deal with real signals in engineering, it's going to be conjugately symmetric, and negative frequencies are given by the positive frequencies. It's just a weird anomaly of the Fourier transform. And if anybody does get any insight into what negative frequencies are, let me know. Okay. Okay, are there any questions at all? Any other questions? Okay, hearing none, I'm going to close the course, not close the course, I'm going to close the window. We have one more lecture remaining, and we will spend the time as much as you want answering questions and also working the problems. Now, here's a question. Does this help you on that homework problem about taking the white noise and convolving it with the rectangle function? If you take that white noise, and by the way, the discrete white noise, when you generate a bunch of numbers from 0 to a half or 0 to 1, that's going to be a white noise sequence. Okay, it's going to be white. Why is it going to be white? Because adjacent results are uncorrelated, right? The expected value of the product is the product of the expected values, at least in that sense. So you're taking this, and it has an autocorrelation of a Kronecker delta, a single point. And what's the corresponding power spectral density of that one point of that white noise?
We had infinitely many points. It should be a constant.
It should be a constant. That's right. And I want you to assume that it is a constant. Now, we convolve this with a rect. What do we do in the frequency domain?
Multiply.
By what?
I think it's a sinc function.
A sinc, a sine x over x. Remember, the Fourier transform of a rectangle is a sinc function. Now, we don't just multiply by a sinc, but that's the sinc is the impulse response, right? No, the sinc is the frequency response. Sorry. The impulse response is a rectangle. The Fourier transform of that rectangle is a sinc. So what's the output going to be? It's going to be equal to that constant. It's going to be equal to the constant times the sinc squared, correct? It's going to be a constant times the sinc squared. What does the sinc squared inverse Fourier transform to?
Triangle function.
Triangle function. In fact, it inverse transforms to a rectangle convolved with a rectangle, right? So hopefully that will give you a better running start on that one program, on that one problem that I gave you. Now on the, let me just say this. No, I'm not going to say that. I was going to give you some hint concerning generation of the impulse of the autocorrelation, using an ensemble average, but don't think I'm going to do that. Any other questions at all? Okay, hearing none, we will see you next time for one more time. Until then, be of good cheer. Be nice.
Yeah. Everyone.
Somebody got excited.